practice. Alright. Okay, so I don't know if y'all have watched the bit about static electricity. Yeah, maybe not. Alright, static charges and how they interact. But we're going to get soon into Coulomb's law. That's in chapter 1. And Coulomb's law just describes the force between two charged particles. So if I have a charged particle Q and a charged particle little q, there are forces between these two. There's a force here, and then there's a force here. And the magnitude of those forces are given by Coulomb's law, which is K, Q, Q over R squared. If you remember, this looks from last semester, Newton's universal law of gravitation. We had that F equals G nm over R squared. We sort of just glossed over it, but mentioned it in passing. This looks a lot like that. Whereas before you had two objects of mass being attracted to one another, here you have two objects of charge. So some common problems that you'll see when we get to this, and you'll have a Moodle quiz on it next week with Coulomb's law, is what are the forces acting on an object. So let's just do an example first, and I'll sort of show you how this works. Let's say that I have a charge that is 1 times 10 to the negative 9 coulombs. All right, or that would be also 1 nanocoulomb. Remember our metric prefixes, we're going to need to know those. Our nanos and our micros this semester are going to be pretty important. Nano is 10 to the minus 9, micro is 10 to the minus 6. Right? We'll use centi and milli as well, but those small ones are important because we're dealing with small things. So let's say I have 1 nanocoulomb charge, and then just to make the math easy, I'm going to call this 2 coulomb, a 2 coulomb charge. And I want to know what is the force acting on this charge. So what is the force acting on that charge? First of all, the question I want to ask myself is, what is the direction of the force acting on that charge? So what is the force on this charge? Since these are the same sign of the charge, I have a positive charge and a positive charge. Positive charges do what? Attract or repel? They repel from one another. Like charges repel, opposite charges attract. So if I have two like charges, they're going to repel from one another. So I'll have forces in this direction. So the force that I want to know is this force. And so I just calculate its magnitude. So you'll certainly have a very simple question like this with just a couple of charges. And just what is the magnitude of the force. Next we'll do one with 3 charges, and that's more complicated. So this force is K, which is a constant, times the 2 charges, that's 1 times 10 to the minus 9 coulombs, times 2 coulombs, divided by the distance between them. Let's say that this distance is 9 meters. Actually, no, 3 meters. Let's say it's 3 meters. So this is 3 meters, and then that squared. That's just this expression, KQQ over R squared. And K is equal to 9 times 10 to the 9th. That's a constant. That's on that equation sheet, which you're going to have that equation sheet on everything on your exam. So you might want to print it out and just sort of, if there's a notebook that you use or whatever, tuck it inside and then keep it to just keep up with what you'll have available. So these are pretty easy numbers. 9 times 10 to the 9th, 1 times 10 to the minus 9, 2 coulombs over 3 squared, which is 9. The 9's cancel. This cancels, and I'm just left with 2 newtons. Okay? That's a pretty simple one. It could be made more complicated by adding a 3rd charge along the same line. And if you look back at the old exams, sometimes you have that, where let's say I have a charge that is negative Q, I have a charge that's positive Q, and then let's say I have another charge that's positive Q. And I want to know what is the force on this charge. Well, first of all, I want to ask myself, what is the direction of the force? Would the direction on that charge, the direction of the force on that charge, be to the left or to the right, or would there be no force at all? And to answer that question, you want to ask yourself, what is the direction of the force given by each individual particle? So, what is the direction of the force on this charge due to this charge? To the left or the right? The direction on this charge, the direction of the force acting on this charge due to this charge. To the left. It's to the left, right? Because they're opposites, so they attract. So I have a force in that direction. What about the force on this charge due to this charge? The left also the left, because these are similar charges, like charges, so they're going to repel from one another. So the direction of the force on that charge is to the left. I have two force vectors that are acting on it, in that direction and in that direction. Now to find the magnitude of that charge, if you know the distances between them and you know the magnitudes of the charge, you just do this business with Coulomb's law. Alright? And then you add them up. Add up the two vectors. Alrighty? Everyone good with that? Let's look at some 2D vectors, because you're also going to have at least one problem on the test that's a calculation doing 2D vectors. We did this last semester, and we're going to see it again a couple of times this semester. But it's often an area where students mess up, so you don't want to be those students. Let's say that we have charges that are arranged on a triangle or on a square, however you want to think of it. Say I have a charge that is here. Let's just one nanocoulomb. I have a charge here that is 2 nanocoulombs. And I have a charge here that's 3 nanocoulombs. And I want to know what is, I want to make some of these negative. I'll make this 2 nanocoulomb negative. What is the net force on the 3 nanocoulomb charge? All right. Let's say that this is 3 meters, and we'll call this 4 meters. It looks like a square, but it's really a rectangle. Right, 3 meters and 4 meters. Several steps you're going to want to do here. You want to find angles, you want to find distances between those charges that aren't on the side of the square, and then you also want to use Coulomb's law in order to find the magnitude of the charges. I'm going to duck out, I'm going to get my calculator, but right now just draw the vectors that are on this charge due to the other two charges, and I'll be back in about 10 seconds. Where we got two vectors? We have 2 vectors. One of them goes in what direction? To the left. I have one going in this direction. Can you friend, where's the other one?
I have one going straight up towards
Oh, towards that one? Okay, well, this one's positive and this one's positive. So what's the direction? Yeah, it's going to go in this direction. So when I draw my vectors on there, it's a very important step that I draw these correctly. They're going to look like this. I have one going in this direction, and then I have another one going in this direction. Okay, and then I need to figure out what are those angles. So I'm going to redraw this on a vector diagram. I have one force here. I'll call this F1, and then I have another force here. I'll call this F2. All right. And then I need to know what is this angle. In order to do that, I need to recognize that this is a triangle right here. It's actually a special triangle. It's a 3, 4, 5 triangle. Right? You'll know that triangle. And then this angle, I always forget what that angle is. But we can find that angle is the inverse tan of 3 over 4. 37 degrees. Are y'all okay with that on the trig? Finding the angles of these. Remember, you'll need to remember your trig functions because that all comes into play with the vectors. So if I want to, I'm going to sort of develop that triangle over there, that 3, 4, 5 triangle. This is 3 meters, this is 4 meters. I know that the hypotenuse is 5 meters because the square root of 3 squared plus 4 squared is the square root of 25, or that's equal to 5. But it's really just something that you should know because that's a triangle that I often use because it's easy to use. Alright, so that's a special 3, 4, 5 triangle. And then this angle is 37 degrees. If you forget, like I often do, you can do the inverse tan of 3 over 4, and then you'll find that's equal to 37 degrees. I do that because I know that from SOHCAHTOA that the tan of opposite over adjacent, or excuse me, I'm sorry, the tangent of theta is equal to opposite over adjacent. Alright, so when I solve that for theta, I take the inverse tan of both sides and I find theta, and that's what I did here. Okay, it comes up here, and then it comes up again when we do electric fields. So we're still going to see this for a bit. When we get into geometric optics, have a little bit more trig at that point. Okay? It's okay to be weak in trig. It's not okay to not improve. All right, so if that angle is 37 degrees, I want to know what is this angle, what is that angle, which is my angle theta. If this angle right here in this triangle is 37, this angle is also 37. Because anytime you have two lines that cross one another, as I do here, I have a line that crosses there and there. These two angles are identical. I think those are, I don't know what those are called. They have a special term for that.
Yeah, I'm sorry to interrupt.
What's that?
I need the car key. I left mine in the car.
Oh, okay. All right.
Sorry.
All right. But you'll bring him back.
No, I'm just
Oh.
gonna take it. I left it in there.
Oh.
Sorry.
That's all right. Okay, guys, y'all with me on this? Yes. Yes. It's important. Like, we did this a lot last semester, but it comes up again this semester. Okay, so if this angle is 37 degrees, now I want to find the x and y components of F2. So I have F1 here. To find the x component of F2, that's going to be F2 times what? When we do sine or cosine, the x component of a vector is what? Is cosine, that's right. F2 cosine of 37. And then the y component is F2 sine of 37 degrees. Okay? Now we want to add up all these vectors, and let's see. Is that right? Oh, that's here.
So why don't we need cosine of the x and y?
Because you have to find the components of that F2 vector. F2 is not on either the x or the y axis, it's in between the x and y axis, and that means that you have part of it acting along the x axis and part of it acting along the y axis. Imagine like you have a rope, right? Like you have a guy pulling on a rope in this direction. He's actually pulling partially in this direction and in this direction. Like if I add up these two vectors, I would get a vector that's the same here. Right, you have both x and y components that are contributing to that vector. Right, I have this, if you go back to displacement, we were talking about displacement last semester, this is my vector. I can also represent this vector as the sum of the x component and the y component. It gets me to the same place if I'm talking about displacement. I can travel this direction, or I can travel along here. So this vector is identical to the sum of these two vectors. And so I want to break this vector f2 into its x and its y components. Okay. Now, at this point, we'll go ahead and find the magnitudes of the forces. Actually, I'm not going to do the math here because I think we're okay with the math. Are y'all okay using Coulomb's law? That is, just to remind you, doing this step. So actually calculating what the forces are. Would you rather me do the steps? Yes? Okay, I'll do all the steps then. Alright, so I want to now find out, sort of take a little aside over here, and find out what is F1 and what is F2. And F1 is going to be K times Q, which is 3 nanocoulombs, times 2 nanocoulombs, divided by r squared, which is 4 meters squared. So that's just my Coulomb's constant, that 9 times 10 to the 9th, times the two charges divided by the distance squared. Let's see. When we're done with this one, I'll show you a problem like on an old test, for example. 9 divided by 16. I get 3.4 nanonewtons. 3.4 times 10 to the minus 9 newtons. Alright, so that's my F1. This is 3.4 times 10 to the minus 9. Usually on the test I try to have easier numbers. And then I want to do a similar thing where I find F2. I'm going to say K. That's my 9 times 10 to the 9th value. It's Coulomb's constant, it's called. F2 is going to be 3 nanocoulombs. That's 3 times 10 to the minus 9 coulombs times this charge, which is 1 times 10 to the minus 9, divided by the distance squared, which is 5 meters squared. You guys follow me on this? How this is tracking along? Now on the test there will be slightly fewer steps, but it's good to go through these steps now, and you'll also find there's a homework question that's very similar to this, but you will certainly have a question that's dealing with 2D forces on the test. Alright, so if I just plug this in, I get 9 times 10 to the 9th, that's K. I get 1 times 10 to the minus 9. I actually get 1.1. I should do 1 times 10 to the minus 9 newtons. So that means that this is equal to 1 times 10 to the minus 9, and this is equal to 1 times 10 to the minus 9. Okay? So now, if I plug this in, over here, I have a vector that's 3.4 times 10 to the minus 9. Over here, I have a vector that is 1 times 10 to the minus 9 times cosine of 37. I get 8 times 10 to the minus 10. And then down here, I get a vector that's 1 times 10 to the minus 9 times sine of 37. Which I get 6 times 10 to the minus 10. Okay. Now, I'm going to add these vectors up. That means that this one's in the x direction, negative x, this one's in the positive x. But since this vector is bigger, the sum of those two vectors will be in this direction. So that's going to be 3.4 times 10 to the minus 9 minus 8 times 10 to the minus 10. That's 2.6 times 10 to the minus 9. And then the y component is still the same. Alright, that's a lot of work, right, to get down to this point. Now, on the test, there will be fewer steps, and I'll show you how that is. But the steps are all still the same. Like, you'll have fewer vectors to deal with, and I can show you how that'll be made simpler for you. But the steps are still all the same. Corinne?
So the negative is the first part in the original problem, negative 2 nanocoulombs. Is that just to tell us the direction of the force? We don't use that in that.
Right here are, yeah, very good question. Often students get this messed up. You don't actually put in the sign of the charges whenever you're putting them into Coulomb's law. All right, so at no point did I put in a negative 2 nanocoulombs. Like here, for example, I put in positive 2 nanocoulombs and not negative. And the reason for that is because the negative comes into play right here when I draw the direction of the vector. So if this was a positive charge, I would have drawn this vector in this direction. But since this is a negative charge and this was positive, I draw it in that direction. It's an excellent question, and often students mess it up. And actually on the test, like, you'll have options where that mistake is made. Okay. Oh goodness, it's all a jumble. All right, so now we have two vectors, and now I just want to know the magnitude and direction of those two vectors. I know that they're going to add up to give me a vector in this direction, right, because they're in the negative x, negative y direction. It'll put it in the third quadrant. And so if you remember, to find that magnitude of the vector, I say 8 times, or 2.6 times 10 to the minus 9 squared plus 6 times 10 to the minus 10 squared, and then square root all of that. And that's going to be about 2.6 times 10 to the minus 9. Turns out that smaller vector isn't really going to impact it much at all. It might be like 2.6 something times 10 to the minus 9. So that would be your magnitude, huh?
What is 8 times 10 raised to the negative 10?
Okay. The 8 times 10 to the minus 10 came about right here. It is the x component of f2. So we found the magnitude of f2 to be 1 times 10 to the minus 9. And then we multiply it by cosine of 37. All right. All right, so now that we have the magnitude, that's one part of the answer. Now we also need to know this angle, all right, which is phi. And if I want to find that angle phi, look, I have a triangle here. I have one vector here, and then there's my resultant vector. All I've done is I've just shifted this over to that side. That's my angle phi. This is 6 times 10 to the minus 10. This is 2.6 times 10 to the minus 9, and I just do the inverse tan of opposite over adjacent. That's 6 times 10 to the minus 10. It's going to be a really small angle, I think. I get 13 degrees. And then that's the answer. 13 degrees below the negative x-axis. It's a lot of steps. Obviously on an exam you wouldn't have that many steps. I would try to make it simpler, because on the multiple choice exam, the more steps you have, the more places you have to make mistakes. But you will have to follow those steps. Let me show you some simpler problems, okay? And then we'll see if you have any questions. Tracking okay though? Please stop me if I'm going too fast. I don't want that. Want to look at some other questions? Is that okay? I'm going to show you some old test questions. And we'll try to aim for about 3:45 to wrap up. Is that okay with y'all? But help session, you can come and go as you like, all right? And as I said, I don't take attendance or anything, so Like if you can't come on Thursday, that's fine. But I've set aside this hour for anybody that wants to come. So I think it's probably better for you to try to come every week than to just come like right before the exam. Let's see, where are we? Those vectors come up again when we do fields, and next week we'll look at fields, but they work a lot the same as forces. Where is it? Okay, so here's a simpler problem. We have this arrangement of particles, and this is spring of last year, 2014, exam 1. I have these 3 particles, and I just want to know what is the direction of the net force on the 3 microcoulomb charge. So the direction of the net force on this charge. And I have a positive charge here, a positive charge here, and a positive charge here. Now remember that first step where we drew the vectors? Right, we're going to do that here. So we should be able to draw those vectors and think about what is the direction of that force, the way the charges are laid out here. So I have 2 vectors. What are the directions of those vectors? Right, I have one to the right. So the direction of the force on this charge due to this charge is to the right. And the direction of the force on this charge due to this charge is down. Because they're all positive and they're all repulsive forces. So I have one vector in this direction and one vector in this direction. And then we further look at it and we see, well, we have a 3 and a 2 microcoulomb charge interacting here, and a 3 and a 2 microcoulomb charge interacting here. So which of these forces is going to be bigger? These are going to be identical forces. So if I think about these vectors, I can redraw them slightly. I'm going to take this vector and move it over here, and then if I add those 2 vectors up, I'm going to have my net force in that direction. What type of triangle is that? If these forces are the same, it's a what? It's a right, not just a right triangle, but an equilateral right triangle, right? Because the 2 sides are the same, and in that type of triangle, what is the angle? This angle right here. No. No. Well, the angles have to be equal, right? Well, you can look at the right here, right? It's 45 degrees. All right, so I know from the options actually that the answer has to be 45 or along the x-axis. But now the question is, what is the direction of it? Is it below or above the x-axis? It's below the positive x-axis. So the answer there would be A. Okay, let's look at another one where you're actually calculating the magnitude. I think maybe the next one. Oh no. And we'll come back to that. So this is spring 13 exam. Okay, let's look at this one actually. So here I want to know which of these force vectors is the force vector that's acting on the plus 2q charge. Which of these is the appropriate force vector? And on these you'll want to draw out the vectors and then try to figure out which of the vectors represent the sum of those 2 vectors. So the plus 2q charge here has 2 forces acting on it. What's the direction of those forces? up and to the left, right? And what's the other one?
Down from the right,
Down from the right.
or an angle from positive.
Like down and to the left?
Yes.
Yeah, so these two charges are repulsive, so I have a force down in that direction. These two charges are opposite, so they attract to one another. How does the force due to these two charges compare due to the other force vector? It's doubled, right? Because I know that from Coulomb's law, F equals k q over r squared. If I double one of the charges, I double the force. Right? So I know that this vector is going to be twice the length of the blue vector here. All right. It's important because if they were the same length, the answer would be what? It would. The answer here is B. The correct answer is B. But if these two vectors were the same length, this blue vector and this red vector, it would be what number? A. It would be A. If I had two identical vectors, the sum of them would fall in between. All right. There's a lot of vector stuff on this first exam, not just with forces, but also with fields, which we'll get into next week. So that was from, we did a lot of that last semester, but it comes back quite a bit. Let's see, I really wanted to do a different type of problem. Let me look at the previous year.
You just said you ran through.
Oh, yeah, we don't need that. Okay, there's a problem like I was telling you about where you have three charges and you have to find the net force on one of them. We did one similar to that. Okay, here's a good one. So this one is simpler than the one that we did. I have instead of having three charges, I just have two charges, and that makes it a lot simpler to work through. The first one is I just want to know what is the direction of the force acting on this charge, Q2. By the way, this is string 12. Follow along there. Is the charge repulsive or attractive? Here I have a positive charge and a negative charge. It's attractive, so my force is going to be up into this direction. And I can go through and pick out some of these. I have, let's see, 37 from the positive x-axis. This is in the second quadrant, so it can't be 37 degrees from the positive x-axis. Because if I imagine my quadrants, I know that my actual vector is somewhere over here. And 37 degrees would be somewhere over here. So it can't be C. Likewise, for the same reason, it can't be B, 53 degrees, because both of those vectors would lie in this first quadrant. Let's see, I have 127 from the positive x-axis and 143 from the positive x-axis. Both of those are in the second quadrant. 0, 90, 180. Between 90 and 180, I have this 143 and 127. It's good to be able to go through your answers and figure out which ones are not relevant, that you can just get rid of. So now if I want to know that angle, I want to know this angle, let's say, that's going to be theta is the inverse tan of what?
4 over 3.
Is that right? 4 over 3? That's right. That is right. Opposite over adjacent. I'm looking at a triangle here that has a side opposite 4 over adjacent side 3. 57 or 53, you mean that?
Yes.
Yeah, 53. That's 53 degrees. And so what's going to be the right answer? Okay, you want to be careful because if this angle is 53 degrees, that means that this angle is 37 degrees, and I know this angle is 90 degrees. So if I'm looking from the positive x-axis, that means I'm measuring here, and so it's going to be 90 plus 37, which is 127. Really got to be up on your trig on this first chapter. A lot of vector stuff, okay? So if trig is weak right now, we can schedule some time to go over our trig identities and sort of how to deal with triangles and what have you. But not as complicated as the first problem, but still you got to know all those steps. The next question just asks, what is the magnitude? And that's just applying Coulomb's law. F equals k q over r squared. My q's are 2 times 10 to the minus 4 coulombs, 3 times 10 to the minus 5. I'll read that color. Divided by r. What is the distance between the charges? It's a 3, 4, 5 triangle. You can do the Pythagorean theorem if you like, but it's 3, 4, 5. K here is 9 times 10 to the 9th. So I've set it up here, 10 to the minus 4, 10 to the minus 5, and 10 to the 9th all cancel out. And then I have 9 times 2 is 18, plus 3 is 30. Wait, 18 times 3 is 30, 54, divided by 25. So that's approximately 2 newtons. So we can pick out the right answer is 222. Because that's Coulomb's law. But the vector stuff will help you because we're also going to do fields, and fields will do a lot of the same stuff. So sometimes you'll see these vector problems in terms of forces, and sometimes you see them in terms of fields, but they're very similar. Okay? Next week we're going to do fields and some more vector stuff, defining fields and what have you. Those links 1 through 8 for chapter 1. This is still chapter 1 stuff. Will help you if you want to look at it before you come in. Or don't, that's fine. I don't really care what you do. I just want to talk to you when I'm awake. Okay? Alright? Is this helpful for you? Oh, yes. Alright. I want y'all to do well in the class. Alright, we'll stop there. If that's okay. Unless, any more questions? Probably shoot for about 45 minutes. You know, unless like we're about to do a test, and then I'll stay as long as you need me to. But all right, folks.